persone che ci seguono su YouTube, se saranno timide. Allora. Aspetta che sta avviando lentamente. Adesso vado a postare il link. Aspetta, ci sono anche 2 persone qua, Fred e Virginia. Ti passo subito co-host, così già. Hi Virginia.
Hello.
So Virginia is she's listening to us from United States, I think. So
Wow.
we are already rather international.
That's good, right?
Yes, of course it's good.
Very good.
Why should be bad? So 1 second, that I don't know why the line today is a little bit, my computer. I'm complaining about my computer, but I see that I have many things open, so maybe this is why it's slow. I should not complain. Let's see. Oh my God. So 1 second, I'm trying to put the link of the YouTube. It's taking a while. So how are things going? Where are you now, Virginia? I forgot the state.
Hey, can you hear me?
Yes.
Yes.
In which
Okay.
which
Yes.
which state
I'm in
are you?
Yeah, I'm in North Carolina.
North Carolina. Okay.
Right. So I'm at the Army Research Office, but I'm also have a position at UNC Chapel Hill.
Yes. I used to know some. Do you know? Well, he works in Virginia Tech. Mark Streamler. No.
No, I don't think so.
Yes. Okay.
How do you spell it? What department?
Streamler. No, he's in Virginia Tech. And he's in
Right.
engineering, biomechanics engineering.
Oh, okay.
Yeah.
I'll
He
ask
does
one
very
of my
nice research. Yeah.
Okay.
Very
Yeah, I'll ask one of my I actually have somebody from Virginia Tech that I'm need to be talking to soon. So I'll ask. Is it STREAM?
Streamler.
LER?
Yes.
Okay.
Streamler. Yeah. And I lost the page. Maybe I'm looking in the wrong. I'm sorry. I can't find the school web page. He works on, among others, also on topological fluid dynamics.
Really?
Yeah, very, very
That's
cool.
interesting.
Yeah,
Okay.
very, very nice.
Should definitely look him up.
Yeah. And sorry, I'm just still. Okay. Looking for. I lost the web page on our school. Where is it?
So Stefanella, is this is like this lecture series is part of a year-long lecture series?
Oh, it's more than that. Is that every semester we have 3 speakers, sometimes 4,
Ah, wow.
and sometimes we choose a thematic. So this semester, but it's more like some application of complex network more, but not essential. So we choose different thematics. Sometimes is more applied, sometimes is more theoretical, because the public is very varied. The next mini course will be, for example, on application dynamical system celestial mechanics.
Oh wow.
But we had astrodynamics, or we had application to neurosciences also. We have different kind of, we were very lucky. We had a very good speaker.
That's great.
Yes, and yeah, we also have, like last year, we had the speaker from UPenn. There was also working for CDC, and he talked about what is biomath modeling, and especially epidemic modeling. And he gave an excellent mini course of 3 classes.
Who was that? Who was that?
Howie Weiss. And he used to be a pure, well, I think I will desist in opening. It doesn't open the web page, so no YouTube today, because I don't know why they refuse to open the web page. And so
Stefanella, there are 2 persons in the...
I let them in now. So we were great, because you show how, sometimes you have overfitting, and you can have more than one theory to fit your data even perfectly. So you have to have some knowledge of the theory. So it was amazing course. And he showed us some latest modeling about epidemic spreading on even with airplane data. It was amazing. And the guy, a few months later, died. So it was like,
oh wow,
we had the last lecture.
Is that still available on the website? All those different.
Okay, so yes, we have a website for the school, so you will see all the past lecture. We don't have the one of Vivice, because he was with research was still not published. He asked me to take it down, but I have it. So actually, I asked one of his colleagues what they want me to do it, because it's valuable lecture material, and I would like to know, And so I have this lecture on YouTube, but they are not public for the moment, back, because he had asked me before to die to take it out. So, but the other lectures are there. The other lecture,
that would be really great. And it seems like it would be great to be. These are really great lectures. It seems like it would be good to try to advertise more widely.
Yeah. But of course, I'm waiting for someone from his university to tell us. I hope that I imagine that the paper have been published 1.5 years later. I hope so, but yeah. So some of the students, are late. I don't know where they are, but hopefully they will come. But let's start, and I will record it here, because I cannot go on YouTube, because I don't know why it will not open my computer isn't.
Valentina is arriving. She just sent me a message.
Okay, so let's
It's late, but she's arriving. Yeah.
Oh yeah. So we wait for her. And I would like Mattia know that also there are some other colleagues from the States that, like Joanna, maybe Virginia will remember her, from Naval Research Lab, that are watching your video later on.
Okay.
She even asked me, where is the 3rd video? I say, well, it's still not made, the 3rd lecture. So they're really people that okay, here is. Okay, so let me not forget to at least start recording this. on the computer.
Hello.
Hello, Valentina. So I think
Hello.
hello, welcome.
Oh, sorry for the delay. I'm so sorry.
No, you're very welcome. So
Thank you.
So there are some students still late, but anyway, so
Okay.
we can start anyway because many people
Okay.
they're watching it later on. So please,
Okay.
Mattia, for another lecture, we're looking for.
Okay. Maybe you're just
Ah,
seeing
it's
my
you.
screen.
It's you. It's true. Today
No,
is
it's me.
you. It's not Mattia.
Yeah.
It's you.
No, it's me.
Okay, that's great. So the first lecture from Valentina today,
Yes.
Gambuzza.
Yeah.
Yes. Lucia Valentina Gambuzza.
Yes.
Okay,
But,
so it's from University of Catania, of course. So it's a great pleasure to have another Italian speakers. So please, very anxious.
You need to allow me to share my screen.
Yes. Okay, so please.
Oh, thank you so much. Okay, now maybe you are seeing my screen.
Yes.
Okay, so thank you, Stefanella. Thank you for inviting us. And I'm very sorry for the delay, but there was another in-person meeting. So, okay, in the previous week, you have seen, thanks to the talk of Mattia, the way in which two or more units adjust a given property or something to reach a common behavior, a synchronization. And you have seen a way to determine when two or more units in a network can achieve a synchronization. In my lecture today, I will go beyond the global synchronization. So I will show you something more. So, for example, if we have incomplete synchronization, all the units are interacting and the units are placed in a node of the network, and in global synchronization, all the units reach the same value. And but the global synchronization is not the only possible way in which they can interact. Other interesting phenomena could also emerge in a network if we look at some properties of the network itself, or at some properties of the network, of the dynamics of the node. And sometimes these properties are hidden properties of the system which we are considering. Okay, if we are interested in to see this new phenomena, all this type of different behavior are called cluster states. In cluster states, we have a network where each unit, which can be an individual, a robot, a fish, or whatever you want, interacts with the other units in the network through the topology of the system, and the aim is to cooperate in some sense, or to, for example, negotiate some values. So they start to achieve different behavior with different scope. And the first example of a behavior which is slightly different from global synchronization, from a complete synchronization, is exactly the cluster state. In a cluster state, the units of the network split thanks to something, and I will show you the characteristic of the cluster state, splits into groups, different groups, where the individual in each group have the same behavior or have, for example, the same opinion, which is different, which can be different from cluster to cluster. For example, in this picture, we have the individuals interacting on a network, and thanks to some characteristic of the topology of the network, the behavior this individual, this unit, split into 3 different clusters. So we have the unit inside the blue circle, which have the same behavior, have the same opinion. The people, the unit in green, have a different opinion from the blue and from the red, but the opinion inside the cluster is the same. Another way to look at the climate is to look at the key ingredients, the main responsible of the onset of this particular cluster state. And in particular, as I said before, one of the most important things in the analysis of the cluster state is to look at the topology. In the figure to the left, we have that thanks to the topology, the network split into 3 different classes identified by different colors, and the behavior inside each cluster is the same for all the units. On the right, we have a different scenario, which is typical of another particular cluster state, where we have a network which is completely symmetrical, and we have that all the nodes in this network are connected to all the other nodes. And the main difference is that we can distinguish between 2 populations, here indicated with sigma and sigma prime, and the connection between nodes among these 2 populations is slightly different from the connection, the weights, the strength of the coupling inside each cluster. And in this case, the main responsible of the cluster state, which in this case is called the chimera state, is the symmetrical nature of the structure itself. In the third case, but I don't know if we will have enough time to discuss about it, is the case in which the cluster state is a consequence of, for example, a mismatch in one of the network node, and thanks to this mismatch, we have the formation of 2 different clusters. Okay, in particular, we will analyze 3. I will show you 3 different scenarios, and all of them have different characteristics. So the key property of each state is different from the other. In particular, we have chimera state, cluster synchronization due to network symmetries, and finally, remote synchronization. Okay. The term chimera state that backs to the one of the first paper talking about this strange behavior is the one in 2002 by Kuramoto and Babcock. However, the term chimera state was at first proposed 2 years later by Abrams and Strogatz. So here I have just reported the 2 most important papers on chimera states. And in Greek mythology, why the Strogatz and Abrams have used the term chimera state. In Greek mythology, a chimera is a monster, is a strange monster, made of different parts of different animals. In one case, the chimera has a lion head, has a goat bodies, and a serpent tail. So in our context, in our definition, chimera state refers to the onset of an hybrid pattern in which we have the coexistence in the same network at the same time of some part of coherence nodes. So we have some nodes which have the same follow the same behavior, so individual which have the same opinion, and the other part of the network which is incoherent, so each node has his own opinion, has his own behavior. So this is the definition, just a spatio-temporal pattern in a network, and in particular the network is made by identical units. So the only way to obtain this particular state is to look at the characteristic of the topology of the system. This is as I have said, the first paper talking about this hybrid spatio-temporal pattern dates back into 2002. So why this this term, chimera state, this behavior becomes important in a relatively few years? So the answer is that the first model in which chimera state were observed was the Kuramoto model, so a network in which each unit was a phase oscillator, and until a few years ago was considered interesting to look at a network of made of identical phase oscillator, since we're expected that the only possible way in which phase oscillator can interact each other was either to reach or a complete synchronization or a totally desynchronized state. So why the term chimera state? This is just to see that it's not important only the phenomena itself, but also how the phenomena has been called. And the term chimera state was a particular name, so has attracted much interest from the people. And in particular here you can see the total number of publications in each year regarding the chimera state in the last 10 years, and the number of citations in each year for a paper talking about chimera state. So this is clear and evidence now the term chimera state is important as the phenomenon itself. Okay, the setting for the onset of chimera state is a particular setting, and we start from a ring. So we have the teach unit is connected to another unit, and so on. And in this case, we have just a local coupling, and we have for each node a number P of neighbors, in which the number of neighbors is given by the coupling radius, which is defined as P over N. So P is the number of newest neighbors of each node, then is the total number of units in the network. In the extreme case, and the radius is equal to 1, we have a global coupling. So we have that each node in the network is connected to all the other units in the network, which is the mathematical model behind the chimera state. In the first paper by Kuramoto and Babcock, they use phase oscillator, a Kuramoto model, and in particular we have this system in which the natural frequency of each oscillator is identical for all the units. The new term in this equation is the presence of this function G, which represents the kernel function. So the kernel function is give us information on how on the way in which we are connecting the nodes in the network. And in particular, in the first paper by Kuramoto and Babcock, the kernel function was chosen as to be exponential. So the nodes are connected to each node is connected to other units in the network, depending on the distance. And then we have the classical coupling of the Kuramoto model, so the sine function between the phase, coupling function with the sine of the difference of the two phases of two units in the network, plus an additive term, alpha, which is a tunable parameter, so can be adjusted to look at the behavior of the system. This model, the network made by phase oscillator with the Kuramoto oscillator is the simplest model able to show chimera states. And the most important thing is that all the units are identical. So we have that the natural frequency of all the units is the same. The key ingredient for the onset of chimera state is the presence of the kernel function, which in some sense is a function, is a way in which we can decide on how to connect the nodes in order to see chimera state. If you look at these two pictures, becomes more clear the term chimera states, and in particular here we have the setting used by Kuramoto and Babcock. So they use they use an array made of almost 500 oscillators, distributed over an interval of length 1, and we have a periodic boundary condition. We have the alpha, the tunable parameter, which has been fixed to this value, and the coupling strength is has been fixed to equal to 4. The kernel function, as I said before, is an exponential kernel function, so it gives us information on the connection of the units inside the network. In the top panel, we can see the instantaneous distribution of the phases of each oscillators, of each unit of the network, while in the bottom we have the distribution of the actual frequency of each unit. And it's clear that in the first and the last part of the two pictures, we have that the units are coherent, so the units here have the same phase, and in the bottom we can see that have the same actual frequency. And while in the middle, the cloud of these points represent the incoherent part, where we have that each unit has its own phase, and correspondingly each unit has its own actual frequency. So we can distinguish in this plot clearly the two domains, the coherent part and the incoherent one. And this justified the term chimera state, so the coexistence of different type of behavior in the same network, and in particular when we consider the same units for all the network nodes. This is another setting useful for the onset of chimera states, and in particular this corresponds to the one using later, this corresponds to the paper of 2008 by Abrams and Strogatz, in which they consider two population with the same number of nodes in each population, and in particular we have that the coupling inside of between the units inside each population is the same and is fixed, while the coupling among the two populations is slightly different. And this is the model equation. This represents the model equation. Again, we will have a Kuramoto model, so we can distinguish the natural frequency of each unit. Also, in this case, the natural frequency of all the nodes are identical. Then we have the behavior of the two populations. So the contribution of each population is given by the first term. And this is normalized with respect to the number of nodes inside each population. And then we have the dynamics inside each population, which again is represented by a sin function of the difference of the phase. And also we have, also in this case we have the presence of the tunable parameter alpha. And in particular, theta high sigma is the phase of oscillator high in population sigma, so we can distinguish the behavior inside each of the two population. And we have a coupling, which in this case is not a kernel function, but is just a number. But we have different weights of the strength. So K, sigma, sigma I represent the coupling between the two populations, or the coupling inside each population between the nodes. In particular, Kuramoto, Abram and Strogatz have fixed that the coupling inside the nodes in each cluster has the same weight. So they say that it is equal to mu, which is a number greater than 0, and the coupling within the element of the two population is fixed to another number, which is also in this case greater than 0. And in particular, we have a relationship between these two types, these two different coupling strands. And we have that the coupling inside each population must be greater than the coupling of the units within among the two populations. And to look at the behavior of this system, we introduce an order parameter R, and we can define two different order parameters, one for each population, which is simply given by this formula. And thanks to this order parameter, we are able to monitor the coherence of the units inside each population. Okay, here I have reported just one example of this type of chimera state. In particular, we have that population 1 as complete as the units in population 1 reach global synchronization. So we have that the order parameter related to population 1 is equal to 1. And we are just monitoring the value of the order parameter of the second population. So remember that chimera state is the coexistence in the same network of a coherent domain and an incoherent one. So we have that in population 1, all the units have the same behavior. And so we are looking at the behavior of the second population. In particular, the coupling strength of inside the unit of the population and among the units of the two populations need to satisfy an equation. And as said before, we have that the sum between these two coupling strands must be equal to 1, but not only. We have that we can monitor we can adjust one coupling strength with respect to the other by looking at a parameter A, which represents the difference between the coupling strength inside each population minus the coupling strength of the units among the two populations. So in the first case, if we fix the two parameters, mu and ni, the two coupling strength, such that their difference is equal to 0.2, Strogatz and Abrams have termed this behavior stable chimera. So this is the bottom panel represents the behavior of the order parameter of population 2. So we have a stable value, which is less than 1. So we are not in the coherent case, but we have a situation in which the incoherent behavior of the units inside the second population is stable. So we just have a small fluctuation, maybe invisible, just due to the finite size effect. Because in this case, the experiment made by Abrams and Strogatz, they are considering the two populations, and in each population they have 128 units. In the second case, panel B, we have that the two coupling strength, mu and ni, have been chosen such that their difference is equal to 0.28. And in this case, we have the so-called breathing chimera. So we have a small fluctuation around a certain point, and this means that we have the units which start to synchronize, then again their phase become incoherent, and again start to synchronize, and so on. Finally, we have the long period breather chimera, in which the difference between the two coupling strength is equal to 0.35, and we can observe from panel C, in the bottom panel, that the fluctuation of the order parameter in the second population are very large. So we have in some point that the units are reaching a totally desynchronized state, then the order parameter grows and approaches 1. So we are in a situation in which the units try to synchronize each other, and then again the order parameter decreases and reach again a small value, which is the incoherent way, and so on. So this, along with the behavior of the order parameter of the first population, which, as we have said, is totally synchronized, so fixed to 1, represent the characteristics, the main characteristic of the concept of chimera state. And here, for example, if we consider again the case of long period breather chimera obtained by fixing the difference between the two coupling strength equal to 0.35, and the value of alpha, the tunable parameter, equal to this value. Again, we have the two populations with 128 units. Here, along with the long period breather chimera, I have reported also the a timestamp of the phase of each unit in one of the time of the simulation, and you can clearly see from this picture, from the first one in the left, that we have the first 128 units which are completely synchronized, so they have the same frequency, which is represented by these blue dots with the same values. And the second population, we have the incoherence in the second population, and this is clearly evident from, again, from the cloud of these blue dots in the second part of the network. So the last 128 units of our network. And here, just to look at the behavior of the two ordered parameters, I've also reported in blue the ordered parameter of the first population, which is equal to 1. So it is evidence of the synchronization in the first population. So this is the way in which we can observe the concept of chimeral state, and in particular, the most fascinating characteristic of this state, the chimeral state, is that we can obtain this particular state starting from a perfect symmetry in the structure. So again, we are considering the two population. The units inside each population are connected with one another, and we have also that each unit in each population is connected to all the other units in the other population. In this case, in this particular case, we have that the coherent domain. To the coherent domain belongs the first population, while the incoherent domain is represented by the second population. However, which population is synchronized and which not strictly depends on the initial condition of each unit. Again, chimeral state. So we have that in this state there is the coexistence of a global state in which all the units are synchronized. All the units of the network are synchronized, and this means that for the same set of parameters, if we run again the simulation, so just by changing the initial condition, we can observe a complete synchronization among all the units in the network. So we can have a complete synchronization also between the two different populations. The way in which the chimeral states are analyzed is passing through a method which is called in the literature as Ott-Antonsen reduction. And in particular, thanks to the Ott-Antonsen approach, the system of n differential equation, so we have a differential equation, each one for each unit of the system. So the complete system of n differential equation is fully represented, can be fully represented just by two equations that can be analytically studied. And the two equations are reported here. So we have the dependence on of these two equations from the amplitude, R, and from the tunable parameter, alpha, which can be fixed at the beginning, and also strictly depend on the choice of the two coupling strength between and among the units in the population. So it depends on mu, on the choice on mu and on mu. Psi represent the phase difference between the two populations. So, thanks to this approach, we can easily analytically study our system.
Valentina, scusa,
Yes.
sono due R differenti o è lo stesso R qui? Sono...
Oh, okay, I don't remember if it is, no, it's the same. is the same.
It's the same.
Okay, it's the same here, but I would like to check it. I don't want it's just a typo. Okay, I will check in the paper.
Because there's supposed to be 2 equations. Just okay, you can check later. Go.
Yeah. Okay, we define one of these for each population. So we have the first one for the first population and the second one for the second population. Okay, so we have 2 different equations. Each one is representative of each population. Okay, I miss here the term 1 and 2.
Thank you.
Sorry for the mistake. Oh, okay, so we can derive the state that we are seeing right now. So the different type of chimeras, just looking at the behavior of these 2 parameters. Okay, I want to change a little bit the setting. So here we are considering a ring with non-local coupled units, and in particular we can say that each unit of this ring is connected to 2 P nearest neighbors. So we have P neighbors for each side. Okay, so in the figure, for example, we have that P is equal to 2. So we have just 2 connections by side. And the system equation can be represented in this way. So we have the dynamics of the units plus the coupling function. And the coupling function is represented by this function H. In our case, I just want to show you a different setting with different units dynamics, and in particular we are considering the second order dynamics, so the Fitzhugh-Nagumo. So we have 2 equations for each node, and the first part represents the dynamics of the Fitzhugh-Nagumo oscillator, and the second part is the coupling of the ring with the non-local coupling. And in particular, in this case, we have that the coupling function, the kernel function that we are using, is a matrix in which we have the presence of both direct and cross coupling between the 2 state variables. So B XX means that we are connecting, we are the coupling in the first equation is given by the interaction of the first variable through the first variable of the other units. The second term, the cross term, means that we also have a coupling between the 2 variables. So in the first case, we have in the first equation, we have introduced the coupling of the difference between the second state variable, okay? And this is the strength of this coupling is given by this term, and so on. So to the end, we will have a matrix with these 4 terms. And okay, we again monitor an order parameter. It's the same as before. So a parameter which gives us some intuition on how is the behavior of the units inside the network. And if an oscillator, if a unit belongs to the coherent domain, the order parameter approaches the value of 1, so we are in a coherent case. And in the case of incoherent domain, we will have a smaller value of the order parameter have. And to define this order parameter, we need to define heat over a particular region. So we are monitoring just a portion of the ring. So we are monitoring just the nodes centered in the unit I, and with a region which is less than this value, which is a threshold. Okay, so we want to monitor the spatial coherence of the units inside the ring. Okay, if we consider a ring with 200 units with a non-local coupling function of the Fitzsimmons units, and we consider also that each unit has 70 is connected to other 70 units for side by side. And for example, in this case, we fixed the parameter, the coupling strength sigma, and also beta, which is a parameter of the dynamics. We can have this type of behavior. So this is the part in red is the coherent part, so in which we have that the local parameter is almost equal to 1, so approaches the value of 1, and all the other values means that we have a smaller value of the order parameter. And if we represent just a snapshot, so a window of, so we fix the time and we plot with the dots the variable, the second variable of our system with respect to the 200 units, we obtain that in the middle we have that the units has almost the same value. So we have a small fluctuation, but we can say that in this part we have we can identify the coherent domain in our system. While the other two regions, the two clouds, correspond to the incoherent domain. And again, we have boundary conditions, so we can consider all the points in the clouds as an unique incoherent domain. So in this case, with this particular the particular choice of the parameters, so the coupling strength, in the number of neighbors, in the locally coupled rings, we can obtain a chimera state in which we have just one coherent domain and one incoherent domain.
And what about the other variable? There will be
has
also...
the same, yes, has the same fluctuation. So you can see that in the coherent domain, the value of the units, the first variable are almost the same, while in the incoherent domain they fluctuate between -1 and 1.
Okay.
Yes.
Okay, thanks.
So is equivalent to plot the first or the second variable. Just the second variable has a big fluctuation. So the incoherent domain is much more evident. Okay.
Okay, thank you.
Very sorry for the noise. Okay, but we have a problem with the chimera states, and in particular, as we said some slide before, starting from a different choice of the initial condition of the units, we can obtain a totally different behavior, but but not only. We can also have a sort of traveling behavior of the chimera state, and in particular here, for example, you can see two different initial distribution of the initial condition and two totally different distribution of the coherent domain, which is the in the middle, which is the violet one, and the incoherent one. So one of the most important point in chimera state is how to properly identify the units and how to properly say if a unit at the end belongs to the coherent or to the incoherent domain. And this is a critical point because strictly depend on initial conditions. So the final behavior of your system is extremely sensitive to the initial choice of initial condition. And okay, if another problem, so in this case, for example, we have a number of units, for example, 200, as in the example here, for the fission Nagumo. But if we decrease the size of the system, in this example, we just have 30 units in our system, so we have a number of neighbors which is 14, and again we have fixed the tunable parameter. We can, in this case, there is a problem, and in particular we can say that the chimera state have transient behavior. So at this point, to this time, the chimera state vanishes, and all the units start to all the units are now incoherent. Okay, and this means that we can observe a chimera state if we have a system with a given n. Okay, so we cannot decrease a lot the number of the units inside the system. However, we have in some sense overcome this problem.
So I'm sorry. So in this case, you didn't you were varying during the experiment the number of units?
No, the number is fixed to 30, and surprisingly, after a given time, which is a long time, so we have like okay, the chimera state vanishes. So all the
and so, but there is a critical number for this depends. This critical number depends on the dimension of the system. Depends on oscillation.
Yes, I want to answer to this question with another setting, because we have surprisingly found chimera state in a network of just 10 units. So maybe the most important thing is the initial choice of the initial condition of each unit, and this was a critical point until some years ago. So until some years ago, most of the works on chimera state, they just analyze a network with a great number of units, and they said that below a value, for example, below this value, this critical value, which is 30, the chimera states are just transient. So you can observe the chimera state just for a fixed time. However, by changing the choice of the initial condition, and in particular by changing the type of the coupling between the units, we were able, not only our group, but some people working on chimera state, were able to find the chimera state also in system with a small number of units. So
So, but the domain, the domain will not have to do with the number. For example, here I see from -1 to 1, the size of the domain is now related also to this transient. I mean, this critical N must depend on some parameters, no? Because you find it is smaller. And so
yes, depends on the initial condition of 2 units, so the starting point of this behavior, and also depend on the particular coupling that we are using to obtain the chimera state. As I showed you before, the chimera state, the onset to chimera state is strictly related to the presence of some symmetries in the network. And if you change a little bit the symmetries, so in this case, if you change a little bit the number of the neighbors of each unit, you can obtain a totally different behavior. So for example, in this case, we have a system of 40 units. If you increase the number of neighbors of each unit, maybe you can find a more stable chimera state, okay? So this is a particular case. And I don't know if there are other parameters which are responsible for the life of the chimera state. But sure, I can say that the initial condition and the number of neighbors and the way in which we are connected to the units are the critical ingredients for the onset of chimera state, for the onset of a stable chimera state. So this is particular because at the end of a certain point, we will have that whole the unit collapse into a completely coherent state. But I also just want to say another thing. For example, here we are considering a ring of 200 units. And here I'm reporting the behavior of the local order parameter from 0 to 1000. Okay, so this is the time of my simulation. But I don't know if increasing the number of the units inside the system, we can increase the transient of the chimera state. Okay. So maybe with a value which is higher, with a higher value of the time, maybe at the end, also in this case, we can see that all the units collapse into the same state. Okay, so I don't know if in the real case we have that all the chimera state are just transient, but the time of the chimera state depends on the sides of the system which we are considering.
Thanks.
This is just a counterintuitive example to see chimera state, because I want to briefly show you our experiment, the experiment made in our laboratory, and we have considered a ring with just 10 units, and we arrange the unit just with one connection. So we have that each unit is just connected with one unit in the left and one unit in the right, and we monitor the behavior of these 10 units of Fiziun-Nagumo. In particular, we have implemented the dynamics of the Fiziun-Nagumo in electronic circuit. Here I just reported the schematic of each unit, and this is a picture of our experiment. So all the board, all the units have been designed and have been realized by one student of us in our laboratory. And in the middle, we have all the coupling circuitry. So this is the most important part of our experiment. And on the bottom, you can see all the coupling resistor, which and through this resistor, this variable resistor, we can adjust the value of the coupling between the units in our system. I want just to show you the final behavior. We were able to find this particular state, and in particular by for different value of the coupling strength among the units, we obtain unsynchronized oscillation. So each unit has its own behavior. A phase synchronized oscillation. So we have that all the units follow common behavior. Another state which we have called quiescence and synchronous chimera state, because we have some units, for example, in the top of the panel C, which are synchronized at this value, and the other which are oscillating to a different frequency. And finally, we were also able to see another type of chimera state, which is called the spatially patterned oscillation depth, in which all the units are in oscillation depth. So we don't have oscillation, but the oscillation is different, and thanks to these four types of different state, we were able to classify the different chimera state by looking at different value of the coupling coefficient. Here is the four different chimera state, but here I have reported the behavior of the second state variable of the Fitzhugh-Nagum oscillator for each unit for along the time. So this is just a portion of all the simulation of our experiment. And I just want to go to the end because here we have also characterized the presence and the concept of chimera state, because since we know that the chimera state is in some sense strictly related to the size of the system, we have run for each value of the coupling coefficient 20 different acquisitions. And in order to classify, so in order to have a plot of the probability of the state of each state we have identified in our system. So in order to say that our finding is stable, and that the chimera state that we were found in our experimental setup are not transient chimera state. Okay, we have also looked at the size effect of this particular state, because we have just considered the closed chain. So we have that each unit is connected with just one neighbors in each one neighbor in the left, one neighbor in the right, and we have also considered the case of a closed ring and the case of open chain, in order to see the effect of the condition at the boundary. So the condition of the first and the final unit of our chain. And in simulation, we have found that the chimera state are stable, and in particular here is reported the probability, the occurrence of chimera state by changing the size. This is just in simulation, and And we can say that our system, so both the open and the closed chain are stable by changing the sides of the system itself. I don't know how many time I have. Maybe I need to finish here.
Yeah, we started 10 minutes late, so you can.
Yeah.
Yes.
So I can continue for other 10
Yeah,
minutes.
of course. Yes.
Okay,
yes,
sorry. Okay, so I just wanted to show you the first one was the first attempt of chimera state in electronic circuit in our laboratory, but we did another experiment with a different type of dynamics. In this case, we have considered again a second order oscillator, but in this case we have the Stewart-Landau oscillators, and here we have the setup, the experimental setup we have considered. Also in this case, we have just 10 units. So each board, in this case, we have a totally custom board. So we can arrange how many neighbors we can easily define the connection between the different units, and how many neighbors we can have, will have for each unit. And we can, in this particular setup, we can adjust the value of the coupling coefficient, which in electronic circuit correspond to adjust the value of a resistor, variable resistor, and we adjust this value not manually, but through the use of a computer and a microcontroller. So also in this case, we have studied the ring with just one neighbor for each side, so here m equal to 1, and we were also able to study the ring with 2 neighbors per side. Okay, so in this case I have reported the schematic representation of each unit, which is the core of our experiment, and here I have reported the equation we have implemented in each board, so the Stewart-Landau equation, and again we have the second part, which is the coupling function. In this case, in particular, we have that the coupling between the units has been realized just by using the first state variable. So we have the same type of coupling in the 2 variables. Okay, in this case, we have monitored through 3 different empirical measures. So we have called it M1, M2, M3. So M1 is representative of the average oscillation amplitude across the network. M2 is how the spatially variable are distributed, and M3 capture the amplitude of the average fluctuation of each node, and in particular by looking at the state of the, for example, looking at the first behavior, which is X of each unit in our system, we were also able in this case to identify 4 different states. In particular, we have that the first 2 panels, A and E, refers to the amplitude chimera state. So we have that some units oscillate with this big amplitude, and we have also a smaller amplitude in the other units. In the second case, we have the oscillation depth. So we have that we don't have oscillation in all the units, but in particular we have that the 2 domains for the oscillation depth are such that we have 1 unit in the top, and the second one with the bottom value, the third one again in the top, and so on. So we have the alternance of these two values in our system. Then we have the traveling waves. So we have oscillation of all the units, but is changing the phase of phase in time. And finally, we have the global synchronization, which is a global state in which all the units have the same behavior. Here is the phase portrait in the case of amplitude chimera. So we have plotted the two variables x and y in the complex plane. So from this picture is more clear how is the behavior of the amplitude chimera. So we have the big circles which correspond to the biggest amplitude, and so different circle with different amplitude in our system. And also we have identified a state in which we have one part of our system, for example, node 2, the unit 2, 3, 4, and 5, which are oscillation left, and the node 1 and 6, which are trying to oscillate. So we have a small oscillation in the amplitude, and finally we have the global synchronization among the units 7, 8, 9, and 10. So we have a small number of units, so is not the snapshot of the x variable is not representative of the state, but looking at the spatiotemporal pattern, we can clearly identify the two domains in our system. In this case, we are considering just a ring, so we have m equal to 1. Again, also in this case, we have monitored the occurrence of this state by changing the initial condition, and so we have found, for example, that for a given value of the coupling coefficient, we were able to identify the global synchronization state, which is in blue, with an occurrence equal to 0.4, then the oscillation depth, which is represented by the orange part, then the traveling wave, and then the chimera state, which is the spatiotemporal pattern in which we have two different domains. So the key ingredient of the state, so the coexistence of different states for the same coupling coefficient, is totally true also in our experiment. Okay, here I have just reported the bibliography. So in red, the two starting points. The first one by Kuramoto and Babcock. The second one in which the state is termed the chimera state by Abrams and Strogatz, and then our works on chimera state, in particular the two that I have shown you regarding the experimental evidence of chimera state in small in system with a small number of units. Okay, maybe it's better to finish here. I don't have time to show you the other thing.
Thank you very much, Valentina. Very interesting. So I have a question before to ask.
Yeah.
Do you apply this to opinion dynamics kind of problem?
Okay, yes, in the sense that in opinion dynamics, you can have a lot of individuals. So we have, for example, a portion, a cluster of individuals which have a common opinion, and all the other people that don't believe in this opinion, so they maintain their own the whole opinion, which can be different from each other.
Or it could be the interpret like the opposite. It could be interpreted like they have a democracy, so you have many different kind of opinion, and then someone is driven to people to have just one opinion.
This is very common in real in the real system. Is very common, unfortunately. Yes, in the opinion dynamics, it's very common to see the cluster state, the cluster synchronization. So, in which, for example, the individuals split into different groups, and inside each group have a common opinion, but this opinion is different from all the other groups. I don't know, for example, in a lot of examples which we can apply.
Yeah, because it's very interesting the way one can interpret one thing or the other. Some questions, sorry. Some question people are thanking here. Some question from the audience, because I can keep going on the interpretation of the modeling. In the case here, Mayra Froes from UFRJ is asking you a question here on the chat, and I'm not sure you can read here. In case you've been following the field, how do you feel the state of the art concerning application of the chimera state identification and behavior in current neurobiological research, included in situ in vitro preparation and or non-invasive studies, yet magnetoencephalography studies, in case you are not familiar with a neurobiological contemporary study, what would you advise for neurobiology as a potential hotspot?
Okay, it's very interesting, because I suppose that you can apply the setting of chimera state to a lot of fields. And there is one of them, the first motivation behind chimera state was related to the mechanism of unihemispheric sleep in some animals. So they justify the different behavior inside the hemispheric of these animals with the chimera state. So I think that in the case of the neurobiological research, there are the possibility to apply chimera state setting. And I don't know, for example, in situ in vitro preparation, non-invasive study, I'm not in the field, so I don't know which can be, for example, the possible setting. And now we can select, for example, the coupling, the coupling between the units, so between, I suppose, the units of the biological experiments. So, but in principle, I think that can be applied, the framework of chimera state in this context.
Thank you. So maybe there will be a future possible project.
Why not?
Yes, to think about it, because actually it's very good, because if I understand also, Mayra is learning from one side, and maybe you can learn from the other side, and it's a good actually starting point, because people are more open-minded, you know, they're not to take a new path. And I would be very interested to this interpretation of, as I said the other time to also Mattia, to opinion dynamic, okay. Because how you interpret the notion of democracy, or to have different opinion or not, or in this case, you know, how do you interpret also this different clustering, you know, when is good, when is bad. This is open to many interpretation, and is the richness of the subject, and how you trigger this chimera state. Before I ask about the size of the system, is because I maybe, you know, make a parallel to a totally different problem, where they study two interacting system, and they study how was in PD context, and how the behavior or the dominant species might depend on the size of the system, meaning on the spatial size of the system. So it will be your domain side. and they have been observed something that, you know, if the domain is too small, there is no survival, you know, limited, the two species will not survive. And then eventually you have then one species can dominate the other if for some small domain, not too small. And so you kind of fragmentation could bring to domination of a species that it will not be the dominant species otherwise. So in this sense, I felt maybe, who knows if
about the size,
yeah, in this sense, the domain size, but you're right, maybe in this sense, the domain size is the number of sites and not the dimension, or, you know, translated into discrete words. Yes, okay, no, very, very interesting. So any other question? Or you for next lecture? Yeah, so maybe we'll have more for the next lecture next Thursday at the same time. So thank you very much for this very inspiring lecture, Valentina, and looking forward for the next lecture on Thursday. Unfortunately, the last lecture.
The last one, yeah.
Well, you know, we keep going, and if you can send that also some
article,
of course, because here there are some students here that will be. I will ask them to read at least one of the article, and supposedly one very more introduction article for them, just to take the taste of it.
Okay. So I will send you the presentation along with the paper, the related papers. Okay.
Yes. Thank you very much. So thank you.
Thank you.
And see
Bye.
you on Thursday. Bye.